How are you guys? How are you guys? Have a good weekend?
Yeah.
So Miles, I saw you send me an email. I haven't had a chance to read that yet. Is that just...
I was just wondering if I could if we could meet like at the office hours and do some like extra studying for this upcoming quest.
Sure, yeah. It's at 2 today. So just show up to do Zoom and then we'll go through. There may be some other students too from some other courses, but yeah, we can definitely make some progress. So, oh yeah, I guess it's not time. What time does Verizon have? Let's see here. 12 on the dot. 12 on the dot. Okay, let's stand up and let's get our videos on. I want to see your lovely faces. I want to teach humans. Stretch. Stretch some more. Oh, there's no place like home. Mason, I agree. There's no place like home. There's no place like home. Okay, let's sit back down. Okay, we have what left? We have what left for this class? Our final. And it's not a final exam, it's a final quest. So your grade's going to be based off of 6 quests, which will count 85% of your grade. And then since we torpedoed the project the moment we started going online, I knew getting you guys together virtually was going to be a nightmare for you. And then we'll have our WebAssign. And our WebAssign, I'm hoping the WebAssign will boost grades. Again, guys, it's homework. The WebAssign is homework except for that first quest. The WebAssign is homework. So if you didn't get any WebAssign done, you missed one, let me know, and chances are I can open it up for you. As long as you didn't look at the key first. As long as WebAssign will not let me open it if you've looked at the key. Okay. Today is the last day I teach any new content. On Wednesday, we'll do some cleanup, look at some problems from the homework in section 6.4 and section 6.4, and talk about the quest. Our quest will be this Friday. At 12 noon. For those who want to take it at 12 noon this Friday. I know there's some that would rather take it this Friday than next Friday. How many people would rather take it this Friday than next Friday? Okay, so if you want to take it this Friday, that option is going to be available. Some people might have another test at noon on Friday. I don't know if that's you, but then you'll be taking it next Friday. Or taking a version of it next Friday. Are we all on the same page? Guys, it's not going to be a 2-hour final exam. It's going to be a half hour. Quest, all about integration. Okay, so that's kind of where we left off. Okay, so we justified before you took your quest, which was a nightmare to teach you something before you took a quest on logarithms and exponentials. We showed one of the most outstanding mathematical accomplishments of all time. Pretty much the result that changed mankind. Okay, the fundamental theorem of calculus. How many people kind of understood the argument at least a little? How many people followed the argument at least a little bit? Okay, so what we were able to do is we were able to do integrals by doing derivatives. Say what I just said.
We were able to do integrals.
Kind of. And so this is the definition of the definite integral. Do not get burned by a true-false on Friday. The definition of the definite integral, it's defined in terms of calculus is about 3 things.
Limits, derivatives, and integrals.
Oh my. Okay, it's defined in terms of a limit, and it's even oh my more of a limit because it's as n goes to infinity, and it's even oh my because it's defined in terms of a sum. A sum is n, k goes from 1 to n. You got f's with some things stuck inside of it, some x sub k's, times delta x, where delta x is b minus a over n, and your x sub k's are equal to a plus k times delta x, for k equals 0 to n. You've written this down like 6 times already in this class. I assigned some homework where you actually had to do these Riemann sums for like n equals 2 and n equals 5, and it was still a pain. Chances are you're going to have to do something like that on Friday for n equals 4. You're going to have to do something like that homework that was in 5.1. Sorry, in 6.1. Or maybe it's maybe it was 6.3 for Friday. Okay, the fundamental theorem of calculus says you can bypass this infinite limit. What did I just say? I forgot to put on a JMU shirt. I just grabbed a shirt right off the top. Little did I know which shirt I was grabbing until I got and looked at myself on the camera and was like, that does not spell JMU. That does not spell JMU. This is my beach shirt. It says coffee, beach, blank, repeat. Okay, so let's just pretend that this has been blotted out by the people that blot stuff out. We can completely bypass having to do the infinite limit. How many people would like to bypass having to do the infinite limit to get the definite integral? Yeah, me too. Provided you can find a function, say what I just said,
Provided you can find a function.
Whose derivative is f of x. Provided you can find a function whose derivative is little f of x. If you can find a function whose derivative is this guy, then doing this infinite limit can be done by just taking that function, sticking that number in, and minus sticking the a in. And it's just that simple. Even more importantly, there's no error in this. There's no error in this. So if you can find a function so that when you take the derivative of it, you get this function, it's not hard to find the area under the curve. You just plug the b into that capital F, you plug the a into that capital F, and you subtract the two. And you're done with finding the area. So,
Dr. Warren, what does that say at the end of that?
okay, we're all going to agree to be lazy. Do we all agree? How many people are going to agree to be lazy? Because Dr. Warren took away what on all of your quests? Dr. Warren took away what on all of your quests? A calculator. So we're going to be lazy. We're all going to agree that if we write the function, capital F of x, and we draw a straight line down, not an integral sign. This is a straight line. At the top of the line is the
E.
At the bottom of the line is the
A.
A. We're going to agree together in Dr. Warren's calculus that this means the same thing, that you plugged B in, you plugged A in, and you did the subtraction, but you never have to do it. Do we agree? Do we agree? Because at this point, it's just algebra. At this point, it's really just arithmetic. And I don't need to test your arithmetic. You suck at arithmetic. I already know that. Without your calculator, you're screwed. Okay? We plug the B in, we plug the A in, we subtract. How many people agree that line's going to represent that? Raise your hands. If you don't, then you're going to have to do it and plug it in. Okay. Here's 3 properties about definite integrals that are really, really useful. Here's 3 properties. Well, the last one ain't so useful, but the first 2 are really useful. Here's 3 properties. The first property says this. I guess it doesn't say anything, it reads. Here we go. The first property of the definite integral reads, the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. You know, I talked to one that says the exact same thing. No, it's subtly different. This is the integral of f plus g. This is the integral of f plus the integral of g. This is the integral of f plus or minus g is equal to the integral of f plus or minus the integral of g.
Could you read the whole thing again? I can't really read it.
Sure. Thanks, Alex. It's the integral from a to b, parentheses, the function f of x, plus or minus the function g of x, in parentheses dx, equals the integral from a to b of f of x dx, plus or minus the integral from a to b of g of x dx. So it essentially says this: you can distribute integrals across plus signs. Say that.
You can distribute the
Okay, I am not going to hold you accountable. I'm not going to hold you accountable for what I'm going to show you right now. I don't even want you writing this down. What I want to go here is I want to go back to my Riemann sum. And I'm going to be lazy. I'm not going to let n go to infinity. I'm just going to look at it for 4. I'm just going to look at it for k equals 1 to 4. Do not write anything down. You don't need to write anything down. This sum means what? What does that symbol mean to do? Add. You start at 1, you end at 4, and you add them together. So now, I'm looking at a Riemann sum over here where I've got k going from 1 to 4. But now inside this, I've got like my f of x plus g of x. So I've got my f of x sub k plus g of x sub k times delta x. Now, Miles just said that symbol means to add. I start at 1, I end at 4, and I'm going to be really lazy. I start at 1, I end at 4, and in between I put ... Lazy. But guys, could I distribute this delta x across that plus? And could I distribute the delta x across the next one, and then across the very last one? So once I distribute, I'm going to have an f of x sub 1 delta x plus g of x sub 1 delta x. Then there's going to be an f of x sub 2 delta x plus a g of x sub 2. And then I'm going to go all the way to the very end where I've got an f of x sub 4 times delta x plus a g of x sub 4 times delta x. And then what I'm going to do is I'm going to say, hey, everybody who's got an f in it, come over here. So you say that.
Everybody who has an F in it, come over here.
And everybody who has a G in it, come over here.
Anybody that has a G in it, come over here.
We're playing Catholic school. All the boys go to one school, all the girls go to another school. So all the F's come over here, all the G's go over there. But guys, I could write the sum. I would have f of x sub 1 to f of x sub 4. I can write it in summation notation. And the same thing with the girls. I could write them in summation notation. But look, both of these roughly look like this. And that's kind of my justification for why you can just distribute integrals across pluses or minuses. The other major tool is this. If you have a constant times a function, what did I just say?
You have a constant time.
If you've got the integral from a to b of a constant times a function, you can pull that constant multiplier outside in front of the integral. It's the same thing as the constant c times the integral from a to b of f of x dx. So the integral from a to b of a constant of f of x dx is equal to the constant times the integral from a to b of f of x dx. This last one, there's a similar kind of justification for this one I'm not going to do. This last one isn't really very useful, except just in some very small circumstances. You'll run into the integrals sometimes where they'll actually have the smaller number on top, which is not allowed. Like, for example, it should almost always be like the integral from 1 to 7. But sometimes you'll see them written as the integral from 7 to 1. Not the integral from 1 to 7. This is illegitimate. You cannot leave your integral like this. But we can argue that this is the same thing as minus the integral from 1 to 7. If you flip these limits, you just put a minus sign in front of it. If you flip the limits of integration, you just put a minus sign in front of it. And I'll just kind of justify it with this. Our delta x is equal to what? Our delta x is equal to what?
B minus
A over n.
B minus A over n, where b's the upper limit and a is the lower limit. Where b's the upper limit and a is the lower limit. So if I was looking at this, my delta x would be equal to a minus b over n. But pull out a negative, and you get b minus a over n, which is the same thing as minus b minus a over n, which is kind of like giving us our minus sign there. How many people are following? How many people are following? Remember, this is the last day for new material. And you're like, hallelujah, Dr. Warren. Hallelujah. I cannot wait for this class to end. This is my last math class ever, Dr. Warren. This is my last. It started in kindergarten, and it's buried with calculus when I'm whatever grade I am. What grade are you in? What grade are you in? You're not in kindergarten. What grade are you in? Are you in 14th grade? Or are you in 13th grade? What grade are you in?
13.
Who's in 13th grade? Who's in 13th grade? Okay, good. Who's in 14th grade? Who's in 15th grade? Okay, good. Who's in 16th grade? There better not. Okay, all right. Parker's like, okay. Who's in 17th grade? Who's doing the extra lap? Is anybody doing the extra lap? Okay. You know, I heard somebody say at JMU, you know, graduating in 5 years is not so bad. Graduating in 4 is kind of like leaving the party at 10. And I thought, that's not really very funny. I'm like, okay, you know, sorry. If you've never left a party at 10, you're missing, sorry, never mind, sorry. I'm not wearing this shirt either. Okay, stand up, stand up, stand up, stand up. And I'm recording this. Okay, stretch, stretch, stretch. All right, we've done no integrals. So between now and it's now 15 after 12. So in the next 35 minutes, I've got to teach you how to do all the integrals that I assign for homework. That could show up on Quest. That could show up on your Quest on Friday. Or next Friday, depending on which Friday you want.
Dr. Warren, have you already assigned the homework?
Yeah, the homework's already assigned. I'm gonna give.
It's all integrals? Because I haven't seen it on Cengage.
Oh no, I haven't put up a web assign. I've just put it on the on that announcement, on our homework announcement.
Oh, okay. Is it due for a grade?
It's not due for a grade because you guys have a Quest on Friday. So I don't like it. What?
I said, can it be due for a grade, or could we have another?
Who wants do you guys want another web assign? I'll give you another web assign. Who wants another web assign?
It'd be more points, then.
Okay, if you want another web assign, I don't want to beat on you guys though. But if you want me to beat on you, I'll beat on you guys. I will assign a web assign. I'll assign a web assign for due on Wednesday. Okay, I'll assign a web assign. No, due on Thursday. I'll make it due on Thursday because you got your Quest on Friday.
I mean, Dr. Warren, if we're going to be doing the practice anyways, I mean, we had like 2 Zoom sessions before the last quiz. I'm just going to get a good grade.
Okay, I see your logic. I've just never had any students ever ask me for more homework. This is the first in my life where I've heard people like, Dr. Warren, give me more homework. So say that. I'm recording it, so I want this to be
Dr.
recorded.
Warren, first of all,
Dr. Warren, you are giving us more homework.
Okay, now I've recorded that, so next year, nobody's gonna believe me, but I've got this. In fact, wait a second, I need to really record it. Okay, say it again, say it again, say it again, say it again, say it again.
Dr. Warren, give us more homework.
Alright, give us more homework.
Okay. Yay.
Wait, only if it's for a grade though, like a good grade.
Only if it's for a good grade. That sounds a little unethical. Give me a good grade. That's what I'm hearing. Okay, but enough of that. Let's get back to the fundamental theorem of calculus. We haven't done any integrals. How many people are pretty comfortable taking derivatives now? Have I taught you anything? How many people are pretty comfortable taking derivatives? Like product rule. Can you do a product rule? Quotient rule. What's the derivative of e to the x?
E to the x.
Yeah.
Okay, good. I was panicking there for a moment. What's the derivative of x to the fifth?
5x
This is a 4.
What's the derivative of natural log of x? I hope you know that one because I haven't looked at your 1 over x. Okay, so guys, I want to show you that by knowing those derivatives, it really helps with integrals. By knowing those derivatives, and here's one of the properties that's huge with this. If you've got a constant times a function, if you've got a constant times the function, you could use product rule for this, right? You could use product rule, right? You could use product rule. It would be the derivative of the constant times the function plus the constant times the derivative of the function. But what's the derivative of a constant? What's the derivative of a constant? 0. So it's just equal to the constant times the derivative of the function. How many people are following so far? How many people are still in the game with me? Okay, so now, let's talk about the derivative of x to the fifth. What's the derivative of x to the fifth?
5x
to the 4th.
How many people are with me? How many people are with me? Okay, so now what I'm going to do is I'm going to switch this. I'm going to put the 5x to the 4th on this side and the derivative of x to the 5th on this side. Are you going to say that's okay? Is that okay for me to do?
Yes.
So let's do that. Then the derivative of x to the 5th is equal to 5x to the 4th. Do you agree or disagree? Do you agree or disagree? Do you agree or disagree? Okay, but then 1/5 times x, the derivative of x to the 5th, would be equal to 1/5 times 5x to the 4th. Do you agree or disagree? Do you agree or disagree? I multiply both sides by 1/5. What do I get here? What do I get here?
Flash it.
X to the 4th.
1.
Thanks, Miles. X to the 4th. Thanks, Paris. X to the 5th. Okay, now we're going to use this result. Now notice, this is k. 1/5 is k. I'm taking the derivative of x to the 5th. Can I take this constant? Can I take this constant inside the derivative? Is this upper rule true? Is this upper rule true? I'm going to take this constant and I'm going to move it inside the derivative. And so this would tell me then that the derivative of 1/5 times x to the 5th is x to the 4th. Is that true? If you took the derivative of this, would you get x to the fourth? If you took the derivative of this, would you get x to the fourth?
Yes.
Okay, now imagine that you were asked to do this integral. I'm not doing it, but imagine that you were doing the integral from like 1 to 2 of x to the fourth dx. You're trying to find the area under the curve between 1 and 2 of x to the fourth. Now let's use the fundamental theorem of calculus. Can anybody think of a function whose derivative, that when you take the derivative of it, you get x to the fourth? Can anybody think of a function that when you take the derivative of it, you get x to the fourth? And guys, just let me help you. Let's just look right here. Can anybody think of a function so that when you take the derivative of it, you get x to the fourth?
1/5 x to the fifth.
1/5 x to the fifth. Thanks, Jay. 1/5 x to the fifth. Is that true? Is the derivative of 1/5 x to the fifth x to the fourth? So then, using the fundamental theorem of calculus, this is the same thing as 1/5 x to the fifth line. Who goes on the bottom of the line? Who goes on the bottom of the line? Who goes on the top of the line?
2.
2. Now, on Wednesday, you're done. On Wednesday, you're done. Unless it's like a multiple choice. What does the line mean? What does this line mean? What did you all agree that means?
Subtraction.
You put the 2 in for x, you put the 1 in for x, and you subtract the 2. It's f of b minus f of a. Now we're going to actually do it for this one. It would be 1/5, 2 raised to the fifth, 1/5, 1 raised to the fifth, and then I would subtract the 2, and then I would subtract the 2. But this is 32/5 minus 1/5, which is 31/5. And so this would be the answer in the back of the book. This would be the answer in the back of the book. But you guys can stop where on Wednesday? You guys can stop where on Wednesday? At the line. At the line. Because you don't have a calculator. At the line. Okay, now let's see if you learned anything. Let's see if you learned anything. I'm going to change it up on you. So stand up, stand up, stand up, stand up. You need to wake up, I can tell already. You need to wake up. Stand up, stretch, stretch. Okay, sit back down, sit back down. What if you had the integral from 2 to 7 of x to the 8th dx? Suppose you're looking at the integral from 2 to 7 of x to the 8th dx. Now before Newton, you're not going to find this area. Before Newton, you're never going to find this area. Can anybody think of a function that when you take the derivative of it, you get x to the 8th? Because if you can, then we can do this problem pretty quick. Can anybody think of a function so that when you take the derivative of it, I need a function so that when you take the derivative of it, the result is x to the 8th.
1/9 x to the 9th.
1/9 x to the 9th. Take the derivative of that. Take the derivative of that. And when you do, you get 1/9 times 9x to the 8th, which is x to the 8th. Do you agree with them? Guys, do you agree that's a function? So then by the fundamental theorem of calculus, this is equal to 1/9 x to the 9th. Now what do you put? What do you put? What do you put? What do you draw? What do you...
The line.
I saw that, Nick. The karate chop. So chop, chop. Do the karate chop. Come on. No, no, no. I guess the Braves are probably going to lose their name too. No, no. You're a Braves fan. Now what do you put down here? What do you put down here? What do you put down there? What do you put down there?
A 2? Is that a 2?
Yes. And then up there is 7. And we all agree for once and forever that this means I plug the 7 in, I plug the 2 in and I subtract, because you know whatever discipline's requiring you to take this class, when you use this, they're not going to let you leave it at line. Only Dr. Warren. They're going to give you your calculator and tell you do it. But that's not my job. My job isn't to teach you that. Okay, in general, what if x is raised to any power? What if x is raised to any power? I mean, we did it for 4, we did it for 8, but what if it's just a general k? What would that, can anybody think of a function whose derivative would be x to the k? Can anybody think of a function whose derivative would be x to the k? Use the technique that you were just doing. Use the technique you were just doing. It would be
1 over k plus 1 times x to the k plus
1 over k plus 1 times x to the k plus 1, line A and B. Put a box around that. That's your real first integration flashcard. I want you making that a flashcard. The integral of x to any power, the integral of x to any power, because we're using power rule, is 1 over k plus 1, x to the k plus 1, line AB.
Dr. Warren,
Yes.
say we have a constant in front of the x, so it's like 4x. Would it be equal to like 4 times 1 over k plus 1?
Did I pay you, Miles, the head of class, to say that question now? Did I pay you and said, Miles, at this moment, ask that question? Did I pay you?
Yes.
Yes, okay, so yeah, I'll have to pay you later.
Yeah.
I'll settle up later. So no, Miles asked a great question. He asked really an awesome question. Like, for example, let's go back to this. And he said, Dr. Warren, what if there's like and I'm gonna change it, what if there's like 21 x to the 4th? Go back to property 2. Remember we wrote those properties up? Go back to property 2 that we were talking about earlier. What can we do with that c? What can we do with that 21?
Move it in front.
Move it across. It's allowed to go outside of the integral. It's got special power where it can go back and forth. Now, how many people can do this integral pretty quick now? How many people can do this integral? Whose function's derivative is x to the 4th? Well, 1 over 4 plus 1, which is 1/5. X to the 5th, we'll put the 21 out here, line 1 and 2. So yeah, Miles, as long as it's just a constant multiplier, just pull it out and let it hang around outside.
Do we need to know Doc for the quest?
Oh yeah. We're heading there. Yes, you'll need to know how to do that too, Alex. Yep.
In that case, would you mind reading that whole thing again? Sorry.
Sure. It's the integral from 1 to 2 of the number 21 times x to the 4th is equal to 21 times the integral from 1 to 2 of x to the 4th, which is equal to 21. Now we're going to do the integral. 1/5 x to the 5th, evaluated between 1 and 2. And I guess I could even plug them in, so this would be equal to 21. Line means plug 2 in, plug 1 in, and subtract. So, I mean, as far as stuff that we've done in this class, this is probably some of the easiest stuff I think we've done. Once you get into the rhythm of it, it's really reasonably simple. How many people can take the derivative of 2x squared plus 5x plus 7? How many people can take the derivative of 2x squared plus 5x plus 7? And like almost like effortlessly now. It's the same way with integrals. It's just kind of going the other direction. Okay. This one actually confuses kids. And I can understand in the beginning why it confuses them. I don't understand why later it confuses them. Like, for example, give me a lower limit. Give me a lower limit. You guys play with me. You guys, give me a lower limit.
2,
2. Give me an upper limit.
8,
8. Now let's take any constant. So give me any constant. Give me any constant. How's this hard? This isn't hard. You got all the constants in
5.
5. Okay. So imagine that I'm running into the integral. Imagine that I'm running into the integral between 2 and 8 of the number 5. Now let's go back to the fundamental theorem. I need a function. You need a function so that when you take the derivative of it, you get 5. Can anybody think of a function that when you take the derivative of it, you get the number 5 coming out?
5x.
5x. Is the derivative of 5x 5?
Yes.
Yeah, I just said, can you take the derivative of x squared plus 7x plus 5? And you guys are, yes, I can, Dr. Warren. So this is equal to 5x. I draw a line to 8. Now, you don't have to do this, but I just want to do it. I plug in the 8. I plug in the 2. Now this one will actually do. How many people can actually calculate this without a calculator? How many people can actually calculate this without a calculator? What number do you get? What number do you get?
30.
30.
30. How many people got 30? How many people got 30? Okay, now I want to show you. This is actually kind of cool. You know, I talked to Warren, there's nothing about this that's cool. Let's look at the function 5. That's a function that's just always flat. It's up 5. It's always up 5. Whatever, no matter what x is, y is always 5. Here's 2. Here's 8. And here's the area under the curve. This is about the only shape that we can actually figure out without using the fundamental theorem. The one shape we know how to find is a rectangle. How do you find the area of a rectangle?
Length times width.
Length times width. Well, my width is 5. I'm always up 5. My length, how long is it? How long is this?
6.
6. So the area is 30. Is that what the integral gave us? Did the integral calculate that for us?
Yes.
Yeah, so we see the integral's actually doing what it's supposed to do. Now, what if you run into something like this? You're like, oh, Dr. Warren, stop. There's no way I can do the integral. There's no way I can do the integral from 1 to 7 of 12 times the square root of x. That's way, way too hard, Dr. Warren. That's way too hard. Well, what have I taught you guys to do whenever you see a square root in this class? What was your first rule? What is the golden rule?
Turn it into a fraction.
Turn it into a fraction. This is the same thing as x to what power?
1/2.
1/2. So you use the exact same flashcard. You use the exact same flashcard. So I'm going to do this for you. Let's do the Miles trick. We're going to call it the Miles trick. Let's do the Miles trick. We're yanking this 12 out. Now you guys are going to help me out. You're going to do the math. It's 1 over 1/2 plus 1. K's 1/2. 1/2 plus 1. Do the math. Make your elementary school teachers so proud of you. What is 1/2 plus 1?
3/2.
3/2. X to the 3/2. Line, what do we put here? What do we put here? What do we put here?
1 and 7.
1 and 7. And you're done. You're done on Wednesday. You're done on Wednesday. Of course, your book's not going to leave you there. It's going to flip, do 2/3. It's going to do 4 and give you 8. And then it's just gonna plug the 7 in, plug the 1 in, and then subtract. But you guys can stop right there. You guys can stop right there. I want you using your time wisely on the quest. You only have 2 other flashcards to learn. We have 2 other flashcards. Here's the second one. What's the only power of k this would be undefined for? What's the only power of k this will fail? There's only one power of k where this will fail. And what value is that?
-1.
-1. If k is equal to -1, if k is equal to -1, then 1 over k plus 1 is 1 over what? Then 1 over k plus 1 is 1 over what?
0.
0, which is undefined, You're like, Dr. Warren, then what do you do if it's -1? Like, for example, if you have the integral from 1 to 2 of x to the -1 dx, you can't use the power rule. You can't add 1 and divide by it. Well, what does x to the -1 really mean?
1 over x to the first.
1 over x to the first. So this would be the same thing as the integral from 1 to 2 of 1 over x to the 1 dx. You guys agree or disagree? How many people are with me? How many people are with me? How many people are with me? But x to the first is the same thing as just x. Crap. If I only knew a function, if I only had a function that when I took the derivative of it, I got 1 over x, then I could use the fundamental theorem of calculus. If I only knew a function that when I took the derivative of it, I got 1 over x coming out of it.
ln.
Natural log.
Oh, how about natural log? What's the derivative of natural log of x? And you didn't do well on that question if you don't know this. If you don't know, what's the derivative of natural log of x?
1 over x.
1 over x. So this is actually equal to the natural log of x evaluated between 1 and 2. So the only power rule doesn't work for ends up being just natural log. Final flashcard for the course. And then we're going to do a bunch of integrals. And it's not like class ends. Then we're going to do a bunch of integrals. Final flashcard. What if you hit the integral of e to the 7x dx? What if you run into the integral of e to the 7x dx? Like, Dr. Warren, why don't you just make it e to the x? Imagine it was e to the x. Could anybody think of a function whose derivative is e to the x?
E to the x.
So this would be super simple. This would just be e to the x evaluated between 1 and 3. Which is remarkable. I know it's not remarkable to you because you just want class to end. But it's remarkable. That the graph, you think about the graph of e to the x, 1 and 3, and I ask, how much area is there underneath your exponential function? Well, it's just e to the 3 minus e to the 1. Grab your calculators. There's the area. That's amazing that that's just that result. Okay. I'm going to save you pain and agony. Take the derivative of that. We're near the end. You should be able to take the derivative of that. Take the derivative of that using chain rule. Take the derivative of that using chain rule. Take the derivative of that using chain rule. take the derivative of that using chain rule.
Dr. Warrior, genius.
Thank you, Paris. I'm just old, Paris. I'm just old. This would be 1/7 e to the 7x times the derivative of 7x. But what's the derivative of 7x? What's the derivative of 7x? 7. And that gives me, that guy kills that guy, and I'm just left with e to the 7x. So it looks a lot like power rule, but it's not. It's 1/7 e to the 7x evaluated between 1 and 3. It's 1/7 e to the 7x evaluated between 1 and 3. All right, guys. I've got 5 minutes to land this plane into the Hudson. I've got 5 minutes, just like Captain Sully. You don't even know who Captain Sully is, okay? To land this plane into the Hudson. Imagine that you're facing something like this on Wednesday. Imagine that you had a big, nasty integral like this. Now I'm going to read this for Alex. Are you still with me, Alex? Oh, there you are. Yeah, I see.
I'm still here, thank
Okay,
you.
it's the integral from 1 to 2. It's the integral 1 to 2 of 7 times e to the 5x plus 3 times the square root of x plus 4 over x plus 2 over x cubed plus 5x to the 4th dx. You're like, Dr. Warren, I can't do this. Hands on the space bar, hands on the space bar, hands on the space bar. Look at each other and say, wake up. Say, I'm serious, wake up.
I'm serious.
Wake up.
You can do this.
You can do this.
Now say it like you really mean it.
You can do this.
Okay. The very first move I want you to make is to distribute the integrals across all of the pluses and pull out all the numbers that are multiplying in front. So the first thing I'm going to do is I'm going to pull the 7 out using my second property. Pull the 3 out. What should I do with the square root of x? What's the golden rule? What should I do with the square root of x?
Make a fraction.
Pull the 4 out, plus 1 over x. Pull the 2 out, 1 over x cubed. Pull the 5 out, and I'm dropping all my 1s and 2s. How many people could make it that far on Wednesday? How many people could make it that far on an integral on Wednesday? Okay. Now, let's just start doing some of these integrals. If you've got the integral from a to b of e to the kx dx, my last flashcard is this is equal to 1 over k e to the kx evaluated between a and b. That's your last flashcard for the whole course. The integral from a to b of e to the kx is equal to 1 over k e to the kx between a and b. Look up here, guys. Who's the k? Who's the k in this integral? Who's the k? 5. So this is going to be 7 times 1 over 5 e to the 5x, line 1 and 2. You're done with that integral. You're done with that integral. 1/2, have we already dealt with that today? Have we already dealt with 1/2? What is 1/2 plus 1? What is 1/2 plus 1? 3 halves, so it's going to be 3 times 1 over 3 halves, x to the 3 halves, line 1 and 2. Now, of course, if you had to actually evaluate all these lines, this would take you forever. 4. The only power that the power rule does not work for is -1. Whose function's derivative is 1 over x? Whose function's derivative is 1 over x? Natural log of x. Line 1 and 2. We're skipping this guy. We're leaving him right now. Oh, I should have made some, it doesn't matter. I've got the 5 there. This is just straight power rule. Whose derivative is x to the 4th? Whose derivative is x to the 4th? Whose derivative is x to the 4th? 1 over k plus 1. 1 over k plus 1. K is 4, so it'd be 1 over
5 x to the 5th.
1 and 2. Now we're done with everybody. We're done with everybody but this one. You're like, Dr. Warren, how can I deal with the 1 over x cubed? Let me show you the trick. This is a pretty dirty trick. Let me show you the trick. This is the same thing as this is the trick. Is 1 over x cubed the same thing as x to the -3? Is 1 over x cubed the same thing as x to the -3? So you can use power rule again. You can use, what is -3 plus 1? What is -3 plus 1?
-2.
So this is equal to 2, that's that 2. 1 over -2, k plus 1, x to the k plus 1, evaluated between 1 and 2. And guys, it's not going to get any harder than that. It's not going to get any harder than that. It won't even be that hard. The problems I assigned in the book aren't that hard. How many people feel like they can do this? How many people feel like they have a shot at doing this? Okay, between now and Wednesday, I want you doing that homework. I'm going to assign a web assign for Thursday. I'm going to try to pick the exact same problems I picked in the homework. I'm going to try to pick the exact same problems I did in the homework. Okay, I've never, ever once in my life had students ask for more homework. So this is new. I started teaching in 1984 when you were -17, and you're my first class ever to ask me what? Ask me what? What did you ask for?
Homework.
For more homework. For more homework. Okay. We'll meet on Wednesday. We'll meet on Wednesday. Talk about our quest. You have 2 options. Option 1 is you can take the quest on
Friday.
this Friday. Option 2, you can take the quest
Next Friday.
next Friday. I'll probably put out some kind of sign up because I've got to set you up for Zoom to do it. Okay, so I'll probably put some sign up. So you'll have to make a decision probably by Thursday which group you want to be in, whether you want to be in this Friday or next Friday. Tentatively, again, how many people are planning on this Friday? And how many people are planning on next Friday? Okay, I see 1 or 2 hands there, so, okay. All right, guys, thanks for coming and playing. Thanks for coming and playing. Good luck with the rest of your classes. Good luck with the rest of your classes. Vomit on the other side of the finish line. Say that. When you're running a race, don't vomit before you finish your race. Vomit after you finish the race. Say that. Say che. Vomit after you make the goal. Okay. I think I've done enough teaching today. I will see you guys. Thanks for putting up with me.
Thank you.
Hey, Dr. Warren.